Wonderful Indonesia. Have you heard this story?
Excellencies, distinguished guests, participants, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
In the name of Allah, the most beneficent and the most merciful, may peace, mercy, and blessings of Allah be upon you. Good morning, and thank you very much for coming to the second day of the second International Conference on Experimental and Computational Mechanics in Engineering, Icecme 2020. My name is Raihandara Lufika. I am the master ceremony for today's event. I would like to send my gratitude greetings to the Rector of Universitas Syah Kuala, Professor Dr. Insinyur Samsul Rizal M.Eng. IPU, the General Chairman of the Second International Conference on Experimental and Computational Mechanics in Engineering, Icesme 2020, Dr. Ahyar St. MP. M.Eng. The honorable keynote speakers, Professor Luis Casera from University Australia, Professor Yoshikazu Nakai from Kobe University, Japan, Professor Chetan Singh Solanki from IIT Bombay, India, Associate Professor Insinyur T.S. Dr. Muhammad Rizal Al-Kahari from University Technical Malaysia Melaka, UTM, Malaysia. The moderator for Keynote Speaker Season 1, Associate Professor Anupun Terwong Warakul from Kasetsart University, Thailand. Presenters, participants, and the steering committee of the Second International Conference on Experimental and Computational Mechanics in Engineering, Icesme 2020. So, ladies and gentlemen, today's agenda is the keynote speech, which will be delivered by Professor Yoshikazu Nakai from Kobe University, Japan, and Associate Professor Insinyur T.S. Dr. Muhammad Rizal Al-Kahari from University Technical Malaysia Melaka, UTM, Malaysia. And the keynote speech will be moderated by Dr. Zahrul Fuadi, ST MSc, from Universitas Syah Kuala, Indonesia. Before we begin the session, I would like to read a brief profile about Dr. Zahrul Fuadi. Dr. Zahrul Fuadi graduated from the Mechanical Engineering Department, Syah Kuala University in 1996. He joined the same department as junior teaching staff in 1997. Dr. Zahrul Fuadi completed his PhD in the Department of Mechanical System and Design, Tohoku University, Japan in 2009. Dr. Zahrul Fuadi has been conducting researches in the field of friction-induced vibration and tribology for more than 15 years and has published a number of papers in reputable journals. He is currently serving as the Asia Tribology Council, ATC, Vice President for Indonesia. So has joined us today in the studio, Bapak Dr. Zahrul Fuadi.
Yeah.
Good morning, sir.
Good morning. Assalamualaikum semuanya.
Okay. So now we just need to check whether or not Professor Nakai has joined us. Are you with us, Professor Nakai?
Yeah, I'm here. Can you hear me? Can you hear me?
We can't hear you yet, Professor.
Oh, really? Can you hear me?
Yes, no.
Okay.
Okay, thank you,
No.
Professor. How about Professor Rizal Al-Kahari? Are you with us, Professor Al-Kahari? Okay, Professor. Okay. So to begin the sessions, I will hand over the keynote speech, keynote selector to the Dr. Zarul Fuadi. Time is yours.
Thank you. Thank you, ladies and gentlemen. Welcome to this international conference on on experimental and computational mechanics in engineering 2020. Today, we have two speakers, one from Japan, Professor Yoshikazu Nakai. I would say konnichiwa to Professor Nakai.
Can you hear me?
And the other keynote speaker is Engineer TS Dr. Muhammad Rizal Al-Kahari. I would like to say Assalamu alaikum, Prof. This keynote speech will be conducted in panel session. So at first, Professor Nakai will deliver his keynote speech and then continued by Professor Al-Kahari. And we will have some question and answers at the last session after both has finished their talks. So before an outstanding paper in 2018 for Committee on Fatigue, the Society of Material Science Japan. Other than that, he is a member of Fellow of the Japan Society of Mechanical Engineering, Executive Board Member of the Japan Society of Mechanical Engineers in 2009 to 2011, Executive Board Member of the Society of Material Science Japan from 1996 to 2013, and Vice President of the Society of Material Japan in 2011 to 2013, and Chairman of the 8th International Conference on Advanced Technology and Experiments Mechanics in 2011. So today, Prof. Yoshikazu Nakai will deliver a plenary lecture with the title of Evaluation of Fatigue Damage using Ultra-Bright Synchrotron Radiation X-ray. Professor Nakai, thank you for your willingness to become the plenary lecturer in this conference. And I would like to give this screen for you.
Can you hear me?
Prof. Nakai, if you have the preparation, please start this talk.
Can you hear me? Okay, I'm going to start my talk. Thank you very much for inviting me to the conference. I'm going to talk about computed technology, computed tomography, another word, CT imaging. It is a kind of inverse problem in computer science. As you know, it is now widely used in medical management. This CT imaging has been greatly progress using X-ray generated by Can you hear me? So radiation facility. Recent advance of CT imaging using the ultra-bright synchro radiation brought a new world to material science. You can observe interior structure of metallic samples with submicron resolution. Today, I'm going to talk about fatigue damage evaluation by this imaging technique. Now we have third generation synchronous radiation facilities. like this. Third generation synchronization facility means those are installing many devices in storage link. And we employed Spring 8 in Japan. It's located close to our university. You can see it provides highest energy like this. So we have four kinds of imaging using synchronous radiation X-ray. The first one, computed tomography, in other words, absorption contrast imaging is a basic one, and it is now widely used in medical management. And so I'm going to explain others. I mean, refraction contrast tomography, laminography, and refraction contrast tomography. So this is a difference of absorption contrast tomography and refraction contrast tomography. So the principle is something like this. X-ray refract at the interface between components with different lengths like this. This red line shows the refracted beam, and black line shows the direct beam from X-ray source. Just inside of the boundary, I mean this boundary, this region with X-ray beam cannot come. So we have a black region, and just inside of this one we have this white region. In this region, refracted beam and superposed direct beams. So we can enhance the contrast of boundary between two materials. It's also used for the observe the cracks with very small opening displacement. The effect of refraction contrast increase with increasing camera sample distance. It means that no special device are required. Just normal CT system is enough for this contrast. Next, I'm going to explain difference between CT image and laminography. For CT imaging, you have to rotate sample to obtain 3D image. Then the penetration thickness of X-ray is small enough for all directions. It means that only thin bar can be imaged. In case of plate like this, X-ray can penetrate. Thin plate X-ray can penetrate this direction, but X-ray cannot penetrate from this direction. So, for normal CT image, we cannot control CT image. So if you tilt the rotation axis like this, the X-ray penetration depth is always constant, so we can construct the image for thin plate. This is called laminography. Next, this one shows diffraction contrast tomography. When during a rotation of a sample, we have an angle where the black condition or diffraction condition are satisfied. So at that angle, we have a diffraction spot like this. At the same time, extinction spot can be observed in the transmit beam, which is set behind the sample. This spot is usually ignored as and deleted by Nedian filter, but it plays an important role for diffraction contrast tomography. If the grain have no misorientation, I mean the diffraction plane is perfectly flat, the shape of diffraction spot and its extinction spot are corresponding to the projection of grain from incident X-ray direction. Then the three-dimensional shape and location of each grain can be reconstructed by classifying the spot into groups belonging to individual grains. This is a result of this diffraction tomography. This is an example of diffraction spot. During the rotation of sample, you can find several diffraction spots like this. This is the summation of the diffraction spot. Enlarge view of the each one's diffraction spot. Usually, every grain has misorientation due to dislocation. The diffraction and extinction spot image were spread over a range of the rotation angle, and and only part of diffraction grain appeared in a projection image of a fixed rotation angle. Therefore, the contribution from the same grain under each diffraction condition should be summarized for constructing the image of each grain. This is the original diffraction contrast imaging proposed by French group. Our developed method is to use the rotation angle spread, which gives information of misorientation in diffraction plane of individual grains. For diffraction contrast tomography, the distance between a sample and detector, this distance should be short enough to detect the diffraction spots as much as possible. On the other hand, the distance between the sample and the detector should be long enough to obtain large effect of refraction contrast. We developed a dual camera system like this. This camera can move to avoid blocking of X-ray beam for refraction contrast imaging. Using this system, you can observe a crack and misorientation of grains almost at the same time. So this slide shows our previous works for CT imaging this, of the using ultraviolet radiation X-ray. So today I'm going to talk about these four topics marked I read. First one is torsion fatigue. And as you know, propagation behavior under mixed mode loading had been studied a long time. The crack propagation behavior are very complex, including the transition of crack propagation mode. The transition condition must be controlled by the fracture mechanics parameter, such as stress intensity factor, but for surface class, it cannot be calculated without measuring 3D shape of cracks. Fatigue crack initiated under cycling torsion is one example of this mixed mode. The crack propagation under torsion is usually studied through the observation at the surface. and it is difficult to understand the collaboration behavior by conventional microscopies because they give us information only at the surface. Therefore, the mechanism of crack propagation under cyclic torsion could not be discussed in detail. So we applied refraction contrast imaging to observe torsion fatigue cracks. This is the result. It's a optical microcross observed from a surface. You can see the branching like this. This figure shows the CT imaging by using ultraviolet synchronization facility. You can see also branching like this, and like this. So this shows the change of stress intensity factor during the fatigue process for several cracks. I don't want to go in detail, but I just mentioned the branching condition can be determined uh, by the stress intensity factor like this. Okay. Next, I'm going to talk about the corrosion pit and corrosion fatigue cracks. As you know, the degradation in strength is sometimes very severe in corrosive environment, and this is usually attributed to the generation of corrosion pit. In most cases, the shape of corrosion pit is considered to be semi-spherical. However, the shape in aluminum alloy is very complex, like this. Okay, so like this. Uh, this one is observed by replica, and the growth behavior of this kind of corrosion pit has not been clarified yet. So we observe the change of shape during corrosion fatigue. These are of the CT imaging. The blue region shows inclusion, and the red regions are corroded area. You can see the extension of corroded area uh, uh, like this to the around inclusion with the number of cycles. This one shows the number of cycles. So the corroded area extended like this. So it's this phenomenon occurs under the surface, so you cannot observe them from surface of observation. So this slide shows the corroded area and the cracks. In this figure, inclusion is not shown. So you can see the cracks initiate like this. This this slide shows the change of stress intensity factor. Uh, in this case, I don't explain detail, but it shows that the crack initiation um, occurs at a critical value of stress intensity factor of corrosion pit. Uh, I'm going to talk about refraction quantum tomography and inclusion and rolling contact fatigue crack observation.
Excuse me, Prof.
Yes,
Nakai. Prof,
yes.
uh, we
Can you
have
hear me? Hey.
5 minutes. If
Mhm.
it's possible, please shorten your speak. Thank you.
Only 5 minutes? Okay. So I skip this one and uh, so mechanism of rolling contact fatigue is not observed directly by conventional micromechanics. So we employ this one for uh, synchronization method. So this is an example of cracks uh, like this. So you can see crack initiation like this. So the sequence is like this. Crack initiated from the surface, and it grows to the depth direction, and after that, for example, crack uh, if, form at the bottom of uh, the vertical crack like this. So I, I skip this one. So next I'm going to talk about diffraction contrast tomography. This is a change of mist orientation. So the change of mist orientation during fatigue process is different from each grain, and the cracks may initiate from the large change of mist orientation like this. So this is another material. We have it's a CT image of cracks. It's an SM image from surface. We have crack like this and like this. And it's a contrast tomography for this material. You can see grains. We have crack like this. This figure shows a cross section at uh, cross section. We have crack initiated here, and it's a change of misorientation of cracks. Each grain, it's a grain. We have a large change of misorientation like this. Others, the change is very little. So cracks initiated from this grain. So uh, I talk about the result obtained from the 15 years. The imaging technology has been progressing in these years, and it is still progressing. For example, some researchers tried to combine deep learning method with laminography, and they obtain very good results. So we need assistance and collaboration with computer science. It's all for my presentation. Thank you for attention.
Thank you, Professor Nakai. It's a very interesting talk, uh, but we have a very short time. Uh, Prof. Nakai, would you
Yes.
please stay with us for about another 30 minutes?
Okay.
Because maybe after the second plenary, we will have some question.
Okay.
Okay, thank you, Prof.
Okay.
Nakai.
Okay. Okay. Thank you. Thank you
Yeah,
very much.
please give applause for Prof. Nakai.
Thank you.
Thank you. For the second plenary talk, I would like to invite Professor Insinyur T.S. Dr. Muhammad Rizal Al-Kahari. Before we start the plenary talk, I would like to read a brief bio of Professor Al-Kahari. Professor Al-Kahari is a Deputy Director at Center for Strategy, Quality and Risk Management and an Associate Professor at Faculty of Mechanical Engineering, University Technical Malaysia, Melaka, UTEM. He received his Bachelor Engineering with honors from International Islamic University, Malaysia. He was practicing manufacturing engineer in industry for a few years before joining university as academic staff. He completed his MSc with distinction from University of Warwick, United Kingdom. He received his PhD for the research in the area of 3D printing, additive manufacturing from Kanazawa University, Japan. His main research interest is on 3D printing additive manufacturing, particularly related to selective laser sintering or selective laser melting, fused deposition modeling, and wire arc additive manufacturing. He is also certified professional engineers with practicing certificate registered with Board of Engineers Malaysia, professional technologies as recognized by Malaysia Board of Technologies, and global certified lead auditor for ISO 9001-2015. He is also a member of Malaysia Society for Engineering and Technology, Japan Society of Mechanical Engineering, and Japan Society of Precision Engineering, Malaysia Board of Technologies, and International Association of Engineers. Without further ado, I would like to invite Professor Al-Kahari to present his talk. Prof. Al-Kahari, this screen is yours.
Assalamualaikum and good morning. Can you hear me?
Yes, very clear.
Okay, thank you. Mr. and Mrs. Chairman, Rector of the University Syed Kuala, top management of the universities, Professor Yoshizakazu Nakai, professors, academicians, researchers, ladies and gentlemen. First of all, thank you for inviting me to give keynote speaker in ICE-CME. So I appreciate the invitation and that given to me and the time they given to me to give the keynote speaker on the topic on advances in 3D printing. So I will start sharing my screen. So can you get my screen right now? Just to double check.
Yes, sir. Yeah.
Okay.
Yes, if you could highlight your screen. Yeah, okay, that's very nice.
Okay. So I'm as introduced by the Mr. Chairman just now. My name is Muhammad Rizal Al-Kahari. I'm from Faculty of Mechanical Engineering, and currently I'm also attached to a center, Advanced Manufacturing Center, University Technical Malaysia Melaka. So before I go further, I would like to introduce a bit on the Advanced Manufacturing Center, where here we focus on one of the research area, specifically that I'm concentrating is on the 3D printing, or also known as additive manufacturing. So these two names are interchangeably being used. So we focus on various aspects of 3D printing, such as composite material, machine performance, vibration, acoustic, design for manufacture, process monitoring, improved process, tribology, and etc. So all of this we try to integrate by using 3D printing. So we hope that some of you will able to come here, at least to visit UTEM in the future when you are free, and you are welcome to contact me whenever you're coming here. Maybe I can bring you around in Malacca, because currently Malacca is one of the World Heritage. It's recognized as a World Heritage, so there are a lot of historical places here. Okay, so I go straight to my presentation. All of us know about Industry 4.0. So 3D printing has been regarded as one of the important process that which has been recognized as one of the elements required for Industry 4.0. So since then, many research, many works has been done, especially on additive manufacturing or 3D printing. In Malaysia, we have a policy, national policy, what we call as Industry Forward, where based on the Industry 4.0, we have come up with the enabling technologies which will help the country to develop in the near future for in order to achieve Industry 4.0 objectives. So 3D printing or additive manufacturing is one of the core area where the has been recognized will contribute much to the industry and in the research. So some of you may know. So I will go my discussion from the very basics of 3D printing, and then at the end of it, I will highlight the research that has been that have done in the area of 3D printing, and also other area that others might try to do in the future. So 3D printing is not new, but the names just about 10 years back. But actually before that, it is also known as rapid prototyping or solid freeform fabrication. But since 2012, 2011, the name of 3D printing and additive manufacturing starts to be used by the researchers and industry. We can see that in the worldwide, there is an increasing trend for application of 3D printing, especially which is related to metal 3D printing. And we can see from the graph in the slide right now, based on the Wallace report in 2017, the most of the application of 3D printing is on the polymer, followed by metal and polymer, and then metal. But these trends are increasing throughout the world. And then many people interpret one of the process which normally we can find a cheap 3D printer in the market, about a few hundreds ringgit Malaysia, as a 3D printing. But actually 3D printing is a group of process. There are many processes which are classified under 3D printing. It's not one process only. The normally 3D printing that we have seen in the market is what we call as fused deposition modeling. It's one of the process only, but in fact, there are hundreds of process classified, but this process can be classified into 7 main categories, which has been defined by ISO and ASTM. So this process are known as binder jetting, directed energy deposition, material extrusion, material jetting, powder bed fusion, sheet lamination, and wet photopolymerization. So all hundreds of the process can be classified under these 7. So actually in the market, we can find a lot of 3D printing right now. Even students are start using it, but actually they are talking about one of the process only, which is the material extrusion, most of them. Because other process are quite expensive actually for the time being. The cheapest and the easiest 3D printing in the market is based on the material extrusion technology. And one of the technology is what we call as fused deposition modeling, where the material is selectively dispensed through a nozzle or orifice. And if we look at schematically, the difference between this process is as in the slide right now, where we can see that in A is what we know as binder jetting, where the material is being deposited and then being hardened layer by layer. All these 3 processes share the common characteristic, where it starts fabricating a part from the first layer. For example, what I have right now is a sample of 3D printed part. Maybe you can take this one. So meaning to say the part is being fabricated from the first layer until the top layer, which is different from normal fabrication process. And then B is what we call as directed energy distribution. C is material extrusion. This one is the one that we already always find in the market, the simplest one. And we have some sort of filament, and then here the material are being heated and extruded based on the CAD data. D is the sheet lamination, where the material starts from the in the form of sheet, and then it is being cut either by laser or any other means. E is the material jetting. They use some sort of UV light here to harden the materials once it being fabricated layer by layer. F is stereolithography, where the material is in the form of a liquid. And then G is powder bed fusion, where the initial material is in the form of metal powder, so or plastic powder. So it depends. We can change it. So later on, my explanation will be only one of the process only, which is powder bed fusion. So you can see that there are a wide variety of process, but normally people regard the C as the 3D printing, but actually 3D printing is a group of processes. So in UTEM, we have almost all of the process here. We all have a lot of machines because in UTEM, University Technical Malaysia Melaka, our emphasis is more on the hands-on approach, where students are expected to use the machine once during their study. So all of the categories that I mentioned just now, we have the machine here, and students are doing it for their project, for their research, and so on. So these are some of them. You can see the top one, you can get it very cheap, about a few hundreds ringgit Malaysia in here. But as we go along, the price of the machine is higher. This one you can even fabricate on your own right now. You can buy the parts and try to develop anything, produce anything directly. And then if you go further, these are much more expensive machines we can find in the market now: selective laser sintering, directly light processing, binder jetting, material jetting. So all of these are 3D printing also. But as I mentioned just now, people, especially in the layman term, they always refer this one as a 3D printing. But actually, it is cover more than that, more than process. There are a lot of process. Then this one is a much more expensive machine that we can find in the market. We can even print a 3D metal part directly from this machine. We have it in UTEM right now. Some students, my PhD student, using them for fabricating and studying for their research. And this is the stereolithography. So if you can see, if we go through all the process, each and every process and category have their own characteristics, their materials, power source, and strength. So in terms of the selection and the usage of the process, depending on the requirement. So it depends on your requirement, what you're going to use. So last time, 20 years ago, 15 years ago, maybe we are talking about a lot about machining process. But now the way we manufacture will be different. Instead of we machine it, we might produce it once we just require it. So we are moving towards that. So the difference you can see right now, when we are using additive process or 3D printing process, we are producing less waste compared to machining or subtractive process. What are the difference? Actually, there are a lot of difference. Some of them that are very common is in terms of the materials, the speed, complexity, accuracy, geometry, programming, cost, and etc. So once we move from one category to another, we can find a lot of difference in terms of the machines that we are using and the capability of the materials that can be produced from the respective 3D printing machine. And these are the common process of the 3D printing process. We start from the CAD, and then we convert to STL, machine it, transfer to machine, and then we have to set up the machine, build, remove, and then we can actually use the part directly. However, the 3D printing process is not for all of the products that we produce in the market right now. There are certain, or we call as sweet spot for 3D printing. It is suitable if the complexity is high, but the quantity is not that high. I mean, it's in between. So that's where we apply a lot of 3D printing or additive manufacturing. And then if we compare it to a more common process, we can say that additive manufacturing has their own area, not for all process. And then we can see also, it depends on us. 3D printing is not a solution for every product manufacturing, but we are looking towards a more complicated parts, then it is suitable. We have to do some sort of break-even points to when it is suitable to use the process. And there are a lot of applications in mold manufacturing. For example, in my experience last time, when I did my PhD in Japan, I used 3D printing for manufacturing mold. So instead of we machine it by using CNC machine, we use metal 3D printer to produce the mold. And then we can also apply in any in other areas, such as in medical applications, to construct to replace bones or teeth. And in fact, when I did my PhD, one of the students, my next person researcher, is a medical doctor. So not from engineering background, but he is using 3D printing to replace a certain components in our teeth. So the application is wide. And as we know, right now we are having conferencing because of the COVID. 3D printing also being used a lot during this earlier stage of the COVID pandemic, where we produce face shields. I believe throughout the world, people are producing it because the frontliner have problem in terms of getting the what we call large quantity at the same time. And here also we can produce that and give to medical doctors nearby. And in other applications, right here in UTM, because we are very near to the, as I mentioned just now, the World Heritage area, we have a lot of artifacts, and then they would like to preserve it. So in one of the area in our study is that we produce historical artifacts based on our discussion with the museums and the authorities here. We reverse engineering the products, the artifacts, and then we try to produce so that we can show to the younger generations. Maybe you can see that the real artifacts maybe will deteriorate over the time. So that's why we are producing it and try to preserve it. And we can also produce industrial components and so on. Of course, this is to cater the limitation of machining process. Because of this problem, I believe those who have taken some background on mechanical process, they know that these are some of the limitation of machining or subtractive manufacturing, which can be accounted by using 3D printing. So by using 3D printing, there are a lot of advantage, as we can see right now. Rapid product introduction, by just having the CAD data, 3D scan it, we can produce it directly. So, but of course, there are pros and cons when they are using it. But the most prominent advantage of using 3D printing is that we can produce a complex shape. So that is the area where the 3D printing has been recognized worldwide because of the capability to produce complex shapes. As we can see right now, if you use normal process to fabricate it, it's quite difficult. For example, this one is quite we can use machining, but if for the bottom one, we can only produce it by using 3D printing. So these are some of other designs which are complex and almost impossible to fabricate by either process or takes longer time. But however, 3D printing also have some limitation. For example, high porosity, low strength, surface roughness, material compatibility, material availability, and high initial cost. But these are the area which the research a lot being done right now. For example, in my research also, I try to study the porosity of the 3D printed parts. So how we can improve it by doing some sort of modification. And then some of the user come out with the design rules because some of the design cannot be produced directly. So we can see that a lot of industries are currently using it right now. Even in the classroom, teachers are start using it. But there are a lot of challenges. For example, in the technology, software, quality assurance, workforce, and financial. So these are the things that are being discussed, which open up a new research opportunity for us. So, for example, okay, right now I will go deeply on one of the research that I have done last time, but specifically for one of the process only, which is powder bed fusion. So we studied the porosity that produced, because generally in 3D printing, we are not producing the dense part. So the porosity need to be improved further to take the advantage that improve the strength. And then a lot of people try to study and monitor the in process by looking through the what we call as high-speed camera during the process. So we can see that over the time, a lot of people try to observe what actually happens during the 3D printing by looking at the microstructural point of view. So these are some of the setup that I have done last time by using some sort of high-speed camera, and then we develop a system where we can monitor it for selective laser sintering. So, just as we imagine, this is 500 microns. We are looking at a very small area to understand. So it as if a small casting process undergoes here. And then by understanding this, we can develop a process map to understand how we can produce a good 3D printed part. So as we know, when we cross-section the 3D printed part, we can see a layer of material like this. So there are porosity here, which need to be improved and further enhanced. And then these are some of the sectional view from SEM, scanning electron microscope, showing that the part are not dense over the process map or different setting parameters. And then these affect the what we call as the surface roughness of the printed part or consolidated materials that we can produce over the laser power that being used. And then other area of study also, for example, in terms of the permeability, where we try to check the capability of air to pass through the 3D printed part. So we can find that in certain parameter, we're going to get a very dense part like this. But for certain parameter of certain setting, we're going to get a very rough. So this helps us to further understand the process of 3D printing. And then when we are trying to understand, we try to relate to the temperature. So we use some sort of pyrometer to relate the process, the microstructural point of view, and then the high-speed camera image, and try to explain how it happens. So challenges and future direction. So I go to more general information back. What are the areas that we can implement or use 3D printing? Currently, people are using in different areas. For example, just now I'm talking about more on the industrial point of view, fabricating for a mold. but you can even fabricate. We have a group here also trying to do some sort of biofabrication by using 3D bioprinting. And then another group on electronics, printings, and then personal products, and its application to automotive. And recently, we are looking forward to start 3D construction printing. So we are looking forward for that. And then these are some other barriers when we are talking about 3D printing, because relatively is a new process. A lot of things can be done. And then a number of researchers highlight and classify the area where we can go for, we can do research in the area of 3D printing, regardless of what you are doing right now, the area you're doing right now. I believe 3D printing has some parts will help you to doing right now. So I'm still on time.
Yes,
I feel that I
in time.
exceed
In
the time that has to be given. Okay. So as a conclusion from me, 3D printing, additive manufacturing has a wide variety of applications and not only limited to those in science and engineering only. Its impact and research may beyond to social, economics, and educations. And 3D printing is an emerging technology and potential to be used in the future, because people are talking about not anymore mass production, but we're talking about mass customization. So we are producing a lot, but each and every product we are customized based on the customer use. So based on that, 3D printing has a lot of potential there. But there are many technical barriers in terms of the strength, roughness, and so on, as I mentioned just now. But these are the areas that we can do research and work together in the future. Before adoption of a new technology, one must ensure all the requirements are met and fulfilled before using it as a critical component in product development. Because now people tend to replace 3D metal parts, for example, for a critical component. But we have to understand the limitation in terms of strength, capability of 3D printed part before we can actually replace it, or else it might cause some sort of disaster. So by that, I would like to end, and I invite in future, if anybody coming to Malacca and would like to know further on 3D printing, we might collaborate, and you are invited to come here. That's all for me. I pass back to the chairman.
Okay, thank you, Prof. Al-Kahari. It's indeed a very interesting talk. Please, everyone, would you give big applause to Prof. Al-Kahari? Yeah.
Thank you.
Thank you for invitation to visit UTM. And I have several colleges in UTM too, but maybe in the
We have
future after COVID, I will also
numbers of
visit you.
Indonesians here.
Yeah, okay. Okay, ladies and gentlemen, audience, we have some times for question or comments. I would like to invite the audience, if you have any question or comment for either Professor Nakai or Prof. Al-Kahari. Do we have a question from the audience?
Assalamualaikum.
Yes, please.
Waalaikumsalam.
Okay. Yeah. Dr. Zulkarnain, I think, please.
Yeah. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Thank you, moderator. I would like to address my question to Professor Nakai. It was a wonderful presentation, and this is something new for me, according the synchrotron X-rays. So I would like to have more information. What is the difference between synchrotron X-ray and the neutron? Because we have some information also by using neutron scattering. Maybe if we have information that synchrotron can map efficiently the strain and stress at the surface, Is it by using neutron we can map below the surface? Okay, that is my question. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Difference between synchronous radiation and laboratory X-ray is parallelism.
Prof.
Synchronous
Nakai,
X-ray.
would you please speak close to the speaker because yeah.
Can you hear me? The difference between synchronous radiation and laboratory X-ray is brightness. Not only brightness and parallelism of the beam is very important. Synchrotron, the distance between X-ray source and the sample is very large for synchrotron radiation. It's almost 100 meters or 1 kilometer. So the beam is uh, almost parallel. So we can use refraction contrast tomography I showed you the last time. And I, 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 I don't use neutron radiation, but I think resolution is better for synchronous radiation X-ray. But I cannot tell you because I never conducted
Okay.
using neutron radiation imaging. Is it okay?
Yeah.
Okay, thank
Okay.
you.
Thank you. Okay. Thank you for the question, Dr. Zulkarnain. Maybe we have other question from the audience. Okay. Do we have other question?
Yes.
Okay. Yes, please, Pak Dr. Iqbal. Pak Pak Iqbal, Pak Dr. Iqbal, please unmute your speaker.
Halo, Assalamualaikum. Okay. To Dr. Akhatiri, I would like to ask one question. This one regarding what you mentioned before, that several weakness of this 3D printing among all are the surface roughness and the also called as the precision of the shape. My question is actually very simple. Is it possible to overcome this problem by continuing the process of 3D printing with machining process? I mean that maybe we could start with 3D printing process, and then once we get the product, we finish the product by using machining process.
Okay, thank you for the
This one.
question, Doctor. Yes, it is possible. In fact, when I have used in my research before, where in Japan they have one machine, but it's quite very expensive, I believe, the machine. Normally, for 3D metal printing, the most commonly known the fabricator or manufacturer is from German. But in Japan, they developed a machine from one of the manufacturer, Matsura. They developed a machine where a hybrid machine. When after we do the metal 3D printing in the same setup, in the same machine, just imagine our CNC machine. After the laser have irradiate on the metal powder and complete the process, the metal powder already hardened into a metal parts. Later on, from the same machine, the cutting tool will move towards the hardened part. So in the single setup, so that one they regard as the first hybrid additive and subtractive manufacturing machine. So it is possible, as what you have mentioned. In fact, in Japan in 2010, they already have that machine. I believe they developed before that. Because when I used for my PhD, actually I involved a bit on using the hybrid 3D metal. They call it the world first hybrid 3D metal printing and metal cutting in the single setup in the same machines. So it's possible. so that they can improve the surface roughness because of the limitation of 3D printing. So it will fasten the process.
Thank you, Dr. Muhammad Rizal.
you.
And maybe
Thank you.
one other question as a continuing of this question. Regarding the material, is it possible to add some fiber, for example, like we use in injection molding? We can use a purely polymer material, and then we can add some
Yes.
fiber reinforced material.
Yes, it is possible. In fact, in here in UTM also, we have a group which I also involved, looking at adding composite materials into the polymer, and then this will enhance the strength and improve other mechanical properties of the 3D printed material. But of course, there are certain challenge because if we are looking about the material extrusion just now, the nozzle of the machines is very small, so we have to make sure that the added materials are being processed thoroughly and uniformly, so that the material will extrude will not clog on at the nozzle and cause other problems. So it is possible also. Okay, thank you.
Thank you.
Okay,
Thank
you.
you, Dr. Iqbal.
Assalamualaikum, Prof. Rizal. I have one question.
Okay.
Yes.
This is Adnan from UTM.
Okay, please.
Okay, in the literature, I've seen that people are talking about bioprinting, 4D printing and 5D printing in medical application. Maybe if you have any information on that, can you elaborate?
Okay. Okay. When we are talking about 3D, first of all, my friends, Dr. Anand, we met several times.
Yes.
Okay, thank you for the question. When we are talking about 3D printing, it's actually referred to the axis XYZ of the movement of the nozzle. But when we are talking about 4D printing, actually we have another dimensions. In here, what we are talking about is time, where the researchers are studying once we have printed, over the time or under reaction of certain chemicals or other inputs, it will change. For example, we print, maybe we can print, I have some components here. Maybe I print here. Maybe after I put, let's say this is a flower, not just imagine that this is a flower. So once I put inside the water, the flower will change to other shapes. So, or maybe we have studied, we put in other chemicals, or we put under sun, the flower will bloom. So that is the some of the researchers are doing. They are studying how we can design the material, make sure the materials respond and reacts with the internal or other factors that have been given, maybe from the humidity, temperature, chemicals, and other external forces. And they are also talking about in future, maybe, for example, the 3D printed parts can sense the lights, for example, so it will switch on and off automatically. So these are the areas we are talking about 4D and 5D printings. So the number of research in this area is very, people are doing it already, but not still there are a lot of things that can be done. So there are a lot of opportunities in this area also.
So it's referring to more adaptive, right?
Yes.
The product is adaptive to the environment.
And other external forces, elements that being imposed on the 3D printed parts, so that it will change over the time. So
from your what do you call it, understanding, is it the area for the 3D, 4D and 5D printing, is it in the biomedical or traditional engineering?
It can, in terms of application, I believe it can be in the medical and also in the industrial. As I mentioned just now, for industrial, maybe we can produce maybe some components or in maybe in the automotive or some other industrial component that may sense the changes in the process. So changes in the process, so we have some sort of closed loop. It will change automatically to behave something else. So not only, not only in medical, maybe in other area also is possible, I believe,
All
in my
right.
opinion.
Thank you very much.
Okay, thank you, Dada.
Indeed,
Thank you, Prof.
it's very good discussion between you two. It's too bad we have virtual. If we have lunch break, maybe we can continue this discussion. Okay. I would like to invite one more question, maybe directed to Prof. Nakai.
Yes. Okay. Yes.
Yeah. Okay. Prof. Nakai, I have one question regarding this technique. Is it possible, or is there any influence of temperature in the evaluation? Like, for example, if we do this evaluation in the nuclear reactor, where the temperature is sometimes more than 800s, is there any influence on this technique?
No, the imaging is conducted on the synchronous facility, so you cannot observe on site. You can bring them the sample to the synchronization facility, but if so, you can use furnace. You can imaging, but the furnace should be transparent or heated by something like that. So it's a furnace problem. So
Okay.
if there is not this problem, you can imagine it.
Okay. Thank you, Professor Nakai.
Yes, thank you.
Do we still have time?
Yeah.
Okay. Okay.
Okay.
Dr. Rudy, do you want to ask question?
Yes. The question is to Professor Nakai, but actually this one is out of topic of your presentation. We currently developed a single fiber testing machine, like in your lab with Ikram, Dr. Zahrul Kwadi, who is the chair. So the question is, how did you measure the specimen elongation or displacement? What kind
Specimen?
of sensor?
Okay. Usually, it's a depend on material, because thick material X-ray cannot penetrate. Or aluminum alloy, the penetration distance should be less than 3 or 4 millimeters, but for steel, it should less than 1 millimeter. So, but for natural fiber, I think it's very big. Something like
okay.
I never conducted, but it should be more than tens of centimeters. Okay. But sorry, the beam size for our experimenter is almost few millimeters, so you cannot imagine at the same time. So you can divide the sample by portion and portion. Okay.
Okay.
Okay,
Thank you,
Prof. Nakai.
Professor Nakai. I think it's time for us to conclude this plenary talk. Once again, I would like to thank Professor Nakai and Professor Al-Kahari for a very wonderful presentation talk today. Once again, please give big applause for our plenary speaker. Yeah.
Thank you.
Okay, I would like to give back this screen to the Master of Ceremony.
Okay, thank you very much, Dr. Zahrul Fuadi. And I would like to say thank you to Prof. Yoshikazu Nakai for the keynote speech, and we would like to present a token of appreciation to you for sharing your expertise in the sessions. And to present the token of appreciation, we would like to invite the head of Institute for Research and Community Service, LP3M, Universitas Syah Kuala, Profesor Dr. Taufik Fuadi Abidin, SSI MTech.
Professor Yoshikazu Nakai, Kobe University, Japan. We would like to express our deep gratitude for your support as keynote speaker at this conference. Please accept this small souvenir from us. Then the committee will send it to you to Japan. And we also invite you to come to our university later after the COVID-19 pandemic. Thank you very much and see you later.
Thank you very much.
Thank you, Professor Nakai. And then we would also thank Associate Professor Insinyur TS Dr. Muhammad Rizal Al-Kahari for the keynote speech. And we would like to present a token of appreciation as well. And to present the token of appreciation, we would like to invite the head of Mechanical and Industrial Engineering Department, Universitas Syah Kuala, Dr. Irwansyah ST MN.
Professor Muhammad Rizal Al-Kahari from University Technical Malaysia, Malacca, we would like to express our deep gratitude for your support as keynote speaker at this conference. Please accept this small souvenir from us. Then the committee will send it to you, and we also invite you to come to our university later after the COVID-19 pandemic. Thank you very much and see you.
Thank you very much. Thank you also. To the committee.
Thank you. Thank you again, Professor Yoshikazu Nakai, Professor Muhammad Rizal Al-Kahari, and Dr. Zahrul Fuadi. Thank you so much. So, ladies and gentlemen, we would like to have a photo sessions. So, could you please all turn on your video, and then our committee will take the photo for you. To all of you to turn on the video. Okay, then the operator, could you please lead it? Okay, we have taken the photo. Thank you very much. So, ladies and gentlemen, this is the end of the keynote speaker session on the second day of the second International Conference on Experimental and Computational Mechanics in Engineering, Icesme 2020. The next session for attendees is the parallel session, which will be divided into several Zoom rooms. So please refer to your program book for the session details. I am the master of ceremony for today's event. Would like to say thank you and hope you have a pleasant time during the conference. Wassalamualaikum warahmatullahi wabarakatuh.
Have you heard this story about a beautiful place? A place that makes you feel restful. Who live in religious harmony. A place that makes you feel home. that makes you curious for more. Adventure. Start your journey. Travel to the place where the story unfolds. Feel the sea breeze caress your face and the sound of the waves breaking your consciousness. That you can see them through the beauty of woven fabrics. Or smell them through the scent of coffee that wafts in the air. If you have never heard it before, you may now find it intriguing. You may want to know every square inch of this place. From the beauty of its land to the depths of its seas. With an amazing biodiversity. Perhaps you've heard this story about a land which has traditions so diverse. Meet these friendly people who will welcome you with warmth. After all, welcoming guests is their tradition. The light of Aceh, wonderful Indonesia.
Okay, participants and presenters, I noticed that you are still staying in this room, but we will advise you to go to the parallel sessions, which is on your program books, and you can leave these link Zoom for this moment. Thank you. Okay, I would like to tell you one more time that this is the end of the keynote sessions for these for today. I mean, and then you can go to your sessions room for the parallel sessions and presentation. And I would advise you to leave this link zone for a moment. Thank you.
Tajudin, Iskandar, and Shahrija. Pirsa, that's it. Indra already, Zulkarnain already.
If possible, Zulkarnain first maybe, or
Okay. Oh, Miss Ratnasari, can we go to Pak Zulkarnain Jalil?
Gak ada. Iya Pak.
Possible? Oh, ini Mr. Muhammad Ilham Saho, Bang. In this Mr. Muhammad
Pak
tes. Hampir copot nih benangnya. Kamu nyoka pakainya oke, harus pakai dasi. Depan.
Kanan Bapak. Kebanyakan Pak.
Tes 1 2 3. Tes 1. Tes 1 2 3. Tes 1 2 3. Kan ci be untuk masalah malah sayangkin. Uronyan waktu pembukaan suara Pak Rektor kan agak ubit. Iya kan? Menyonyo keban kira-kira. Udah oke nih. Udah oke ya. Tes 1 2 3. Jitnya. Ya. Enggak, maksudnya ada satu orang coba mendengar atau geban. Coba aja dulu. Jangan nanti kan ini kan karena tiba-tiba nih. Tes 1 2 3, tes 1 2 3. Oh iya. Tes 1 2 3 tes. Tes 1 2 3. Jit Pak Mahruza. Kan kami memang uji coba kan untuk B sampai J. Ya. Mau jadi? Tes. Tes 1 2 3. Tes 1 2 3. Oke. Oke. Bagus. Oke, alhamdulillah. Tak ini matikan dulu atau biar di sini terus. Ini aja terus ya. Hanapa punya sambilan jejak hanapa. Oh, get. Hanapa pun coba nyolesat. Oke, oke, oke. Hah? Jadi, hebat.
Nanti saya paling cuma bilang assalamualaikum, kemudian selamat datang kembali di closing ceremony, kemudian saya langsung kasih ke bapak aja. The honor to have the vice rector, and then we would like to ask you to have the closing ceremony. Habis bapak selesai, bapak boleh kasih lagi. Nanti langsung kita.
Nggak, saya setelah assalamualaikum langsung.
Ya.
Waktu saya bilang assalamualaikum warahmatullahi wabarakatuh langsung di tag. Masker harus buka. Cuman kalau bisa nanti untuk ngomong. Nggak. Oh ya, saya nanti langsung.
Have you heard this story about a beautiful place? A place that makes you feel restful. In the midst of people who live in religious harmony. A place that makes you feel home, that makes you curious for more adventure. Start your journey. Travel to the place where the story unfolds. Feel the sea breeze caress your face, and the sound of the waves breaking your consciousness. That you can see them through the beauty of woven fabrics. Or smell them through the scent of coffee that wafts in the air. If you've never heard it before, you may now find it intriguing. You may want to know, have you heard this story about a beautiful place? A place that makes you feel restful. In the midst of people who live in religious harmony. A place that makes you feel home, that makes you curious for more adventure. Start your journey. Travel to the place where the story unfolds. Feel the sea breeze caress your face, and the sound of the waves breaking your consciousness. That you can see them through the beauty of woven fabrics. Or smell them through the scent of coffee that wafts in the air. If you've never heard it before, you may now find it intriguing. You may want to know every square inch of this place. of its land to the depths of its seas. With an amazing biodiversity, perhaps you've heard this story about a land which has traditions so diverse. Meet these friendly people who will welcome you with warmth. After all, welcoming guests
Excellencies, distinguished guests, participants, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. May peace, mercy, and blessings of Allah be upon you. We welcome you once again to the closing ceremony of the Second International Conference on Experimental and Computational Mechanics in Engineering, Icesme 2020, and we hope you have been enjoying yourself at the conference so far. We are honorable to have with us here this afternoon the Vice Rector of Planning, Cooperation, and Public Relation Affairs of Universitas Syah Kuala, Dr. Hizir. And we would like to invite Vice Rector of Planning, Cooperation, and Public Relation Affairs, of Universitas Syah Kuala, Dr. Hizir, to present us with the closing speech and ceremony. The screen is yours, sir.
Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Very good morning, good afternoon. Draw to a close. It is my pleasure to make a few thinking that I believe conference. Especially for the keynote speakers, the first one is Professor Louis Saseta from Curtin University, Australia. We have just signing the MOU with the Curtin University 2 months ago. And the second one, the Professor Yoshikazu Nakai from Kobe University, Japan. With Kobe University, me myself already visit last 3 years, and we already signed the extending the MOU between Kobe University, Japan. And the third one is Professor Chetan Singh Solanki from IIT Bombay. Professor Solanki is a very generous. He visited us here in Syah Kuala University last 2 years. Thank you, Professor Solanki. And Professor Engineer Dr. Muhammad Rizal Al-Kahari from University Technical Malacca, Malaysia. We have UniNet, University Network, in 3 countries, Indonesia, Malaysia, Thailand, and UTEM, one of our network, and the chairman of UniNet right now is Professor Samsul Rizal, director of Universitas Syah Kuala. And also our moderators, Professor Anupun Tet Wong Worakul from Kasesat University. As for your information, Syah Kuala University also already have MOU with Kasesat University. Thank you very much, Professor Anupun. I think it would not be an exaggeration to say that this conference has been a considerable success, where we all too often fear it would be maybe a failure. As you may know, we had prepared for a conventional one, and in conjunction with the University Muhammadiyah Yogyakarta, we at Syah Kuala University in Banda Aceh, we have prepared a wonderful venue and uniqueness scenery. But sadly, COVID-19 struck us and it was not able to be. All those face-to-face meetings and informal discussion were unfortunately lost. However, the task of working on a strengthening applied technology innovation and sustainable development in Industry 4.0 is urgent. So we had to act. We took advantage of this new technology so that we are here now. The participants, almost 100, and coming from various parts of the world, from Malaysia, Japan, Thailand, India, Australia, USA, Taiwan, and Indonesia itself. I would like to thank to everyone who participated, giving so much of their time and energy to helping us and take this conference work forward. Much of this credit must go to the experts who spent over a year preparing the papers that underlay the ideas that we have been discussed. The spirit of lively but courteous debate that characterized this week is a credit to all of us. And then special thanks must go to those committee who work very, very hard behind the scenes. We are also immensely grateful to our university partners, Universitas Teguh Umar, Universitas Malikus Saleh Lok Sumawe, Universitas Samudra Langsa, Politeknik Aceh Selatan, Politeknik Negeri Lok Sumawe, Politeknik Aceh, and Politeknik Kutaraja. And also to state and private company, PT Solusi Bangun Andalas, PT Perta Arun Gas, PT Pupuk Iskandar Muda, and Badan Pengelola Migas Aceh. With that, we bring this conference to a close. Alhamdulillahirabbil alamin. I wish you all well, stay safe, and join in the next conference, Icecme 2021. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Dr. Hizir, for the closing ceremony. And then the next one, we have best presenters. Oh, you may leave if you want to, Dr. Hizir. Thank you very much. So for the presenters, we have best presenter for each session. There are actually 16 sessions in this conference, and for each session we have the best presenter. And for the best presenter, we will announce it through the running text on your monitor. Oh, I apologize. The running tag is not ready yet, so we will announce it to you personally through email later with the certificate as well. Thank you very much. And we will now invite all the committee to come to the studio to officially say thank you for all of you guys for staying 2 days straight with us here in the International Conference on Experimental and Computational Mechanics in Engineering, Icesme 2020.
Ya. Hanya harus naduk setengah badan, Hanya harus naduk sini, besar-besar saja. Sisi wajah. Setengah badan. Badannya pakai masker lah kalau kayak gini. Nyosor ya pakai masker. Pak Jali. Jelas nah, Pak. Oh nah. Muah hana lumah. Lagi ya nah. Hana lumah ulun dia tahu. Sino 02 bawah. Sino 02 bawah. Masuk aja. Ya. Oke dah aman. Assalamualaikum warahmatullahi wabarakatuh. Thank you for all contribution and see you again in next conference in 2020 for 21 ya. For third Icesme 2021. Thank you very much.
Welcome.
Sekali yang terakhir boleh record sebenarnya recordnya. Icesme 2020 sukses nah. And 3 siapa? Record 3 2 nih. Icesme 2020 nanti sama-sama sukses ya. 1 2 3. 3 2 1.
Icesme 2020 will be success. Yeah. Masa bro.
No doa or something.
Excuse me, participants. We have actually excuse me, there's a bit error here. Okay, for the best presenter, we have finished identified the best presenter. So we would like to share the screen for you guys to find out. And of course, later we will email you personally with the certificate. So here is the best presenter for this conference. Okay, here is in the monitor the best presenter for today's for the conference. The first one is Saiful Watan, paper ID 16. And the second one is Amir Zaki Mubarak, paper number 44. And then the third one is Kevin Reynaldo, paper number 23. The fourth one is Arif Saputra, paper number 77. And then the fifth one is Muhammad Iqbal, paper number 105. And the number 6, M.E. Hidayat, paper number 20. And the number 7, Husni Usman, paper number 83. And then the 8th one, Nurul Ismi, paper number 75. Number 9, Mr. Adi Setiawan, paper number 1. And number 10, Mr. Lucas Cano, paper number 68. And then number 11, Nasruddin Abdullah, paper number 73. Number 12, Muhammad Dirhamsyah, paper number 93. Number 13, Iwan Susanto, paper number 80. Number 15, number 14, I'm sorry, Fauzan Rahman, paper number 46. Number 15, Hartomo Suwardi, paper number 29. And the last one, but not least, Zikratul Rina, paper number 5. Thank you very much for joining the conference, and wassalamualaikum warahmatullahi wabarakatuh.